Good morning, class. Here's exam to review covering chapter 3, differentiation rules. And we cover from section 3.1 all the way to 3.8. The first part, 3.1 to 3.3. And here's what we are covering. 3.1, derivatives of polynomials and exponential functions. 3.2, the product and quotient rules. 3.3, derivatives of three functions, and then we move on to the chain rule, implicit differentiation, derivative of log functions, rates of change, exponential growth and decay. Now, again, I want to remind you when we take the exam, although I don't have a proctorio, you take the exam on your own without giving or receiving any help, and that's why there is this pledge. I pledge on my honor that I will neither give nor receive unauthorized assistance, and so on. All right. So we looked at the definition. Okay, the definition, dy dx is the limit of delta y over delta x as delta x approaches 0. Or f prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. This is the good old rise over run or the difference quotient. Now we actually use the formulas. So the derivative of x, in general, x represents the independent variable. Any independent variable we are dealing with would be 1. The derivative of cf of x, c comes out. The derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. In other words, the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. In other words, to term by term, the limit of sine theta over theta as theta approaches 0 equals 1. The limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. And you can look at all the proofs in the lecture. E has a couple of definitions. And as you know, as far as E is concerned, just like pi, it's an irrational number, 2.71, and then it continues indefinitely. So the limit of 1 plus 1 over n to the power of n as n approaches infinity, or the limit of e to the power of h minus 1 over h as h approaches 0 must be 1. So let's see what else we have here. The derivative of a constant is 0. This is called the power rule. The derivative of x to the power of n is nx to the power of n minus 1. The derivative of kx, k is a number, would be k. The derivative of sine is cosine. Cosine is negative sine. Tan is secant squared. Cotangent is negative cosecant squared. Secant is secant x tan x. Cosecant is minus cosecant x cotangent x. I'm giving you the synopsis of the formulas, which will be discussed in various sections, and of course, we will practice with them. What I have here is the product rule, the shorthand notation. Fg prime is f prime g plus g prime f. F over g prime, this is the product rule, is a quotient rule. F prime g minus g prime f over g squared for the quotient rule. And again, this is the shorthand notation. Then we continue with this power rule, and then the extended power rule, which is the result of the chain rule, composite functions. The derivative of g of x to the power of n is n g of x to the power of n minus 1 times g prime. The derivative of e to the power of x is itself. The derivative of e to the power of kx is itself times k. E to the power of g of x is itself times g prime. The derivative of b to the power of f of x, when the base is no longer e. Any exponential, the answer is itself. Then you multiply by the derivative of f of x f prime by the chain rule. This ln b is because of logarithmic properties. And more of that. This is the composite function that was discussed, y equals f of g. So if you want to differentiate, y prime is f of g prime, f prime of g of x times g prime of x. In Leibniz's notation, dy dx is dy du dx. Again, this is the synopsis of the formulas. We will go through them in a moment. The derivative of a natural log is 1 over x. The reason we put in an absolute value because x has to be positive. Okay, if we know x is positive, there's no need for an absolute value. And ln u is 1 over u du dx, and so on and so forth. Again, we will discuss them with more details. Then we get to inverse trigonometric functions. These are the trig functions. These are the inverse trig functions. For example, the derivative of sine inverse is 1 over square root of 1 minus x squared. Cosine would be the same, but it has a negative sign in front of it. Tan inverse gives us 1 over 1 plus x squared. Cotangent inverse would be negative of that. Secant inverse is 1 over x squared of x squared minus 1, and cosecant inverse is the negative of that. So that's the synopsis of the formulas, but let's actually go through them and learn them with a little bit more detail. So starting with this example, and we are covering from 3.1 to 3.4. When y equals x to the power of 1000, we are interested in finding the answer. And I believe most everybody knows. So let's remind everybody of the following three formulas. Number one, the derivative of any number, any constant is 0. Number two, the derivative of k times x is k. The derivative of x to the power of n is n, x to the power of n minus 1. This is the power rule. So according to this third formula, 1000 sits in front. The exponent goes down by 1. So 1000 x to the power of 999. Pretty straightforward. Y equals 3r squared. Bear in mind, the way it's given, the independent variable is r. It doesn't obviously have to be x, okay? So to differentiate this, you keep the 3 and then differentiate r squared, which is 2r to the power of 2 minus 1, and it's 6r. What I want to add here is the notation. Y prime is perfect notation, but when we write dy dr, we are telling the reader what is the independent variable. And that's important. What is the independent variable? And that's why I am using this notation. And now we are looking at this function, and we are going to use the properties that were discussed, meaning if I want to differentiate, I'm going to do it term by term. So we're going to start with the first one. So f prime of x, first one, x to the power of 8. 8 becomes the coefficient. The exponent goes down by 1, 8x to the power of 7. Plus, we bring the 5 down, so 5 times 12 becomes 60x to the power of 4. Same thing here. We bring the 4 down, 4 and negative 4. The product is negative 16x cubed. Plus 10 times 3, 30x squared. Now this one, just like this one, the answer is k minus 6. And any constant gives you 0, and you're done. Now, f of x is x times the square root of x plus 5 minus 2. And I'm reminding you of those basic differentiation formulas. Also, I'm reminding you of exponents, their properties. For example, the zero exponential rule, a to the power of 0 is 1. Negative exponential rules, such as a to the power minus n is 1 over a to the power of n. And specifically, I'm really looking at the product rule because I need to change this to power to the so that I can use the power rule, and therefore I'm going to change this to x to the power of 1/2. And I'm showing you this one, everybody. Square root of x is x to the power of 1/2. And then, so we are going to look at this one first. And now this has exponent 1. We're going to use the product rule. We're going to add these two and we get x to the power of 3/2. This is elementary algebra. Why did we do that? So we get it ready for differentiation using the power rule. So x to the power of 3/2. 3/2 sits in front. We take away 1 from the exponent. 3/2 x to the power of 1/2 plus 5. Now to put it in the same format, this is square root of x. So 3/2 square root of x plus 5. F of x is 2x to the power of 5 over 9x to the power of 9. We can't differentiate it the way it is. We are going to put it in a format that we can use the power rule. And now we are going to use a to the power of m over a to the power of n is a to the power of n minus n. So 2 over 9 is just a number, is a coefficient. X to the power of 5 minus 9 or x to the power of minus 4. Now we are ready to use the power rule. The answer is 2 over 9 times negative 4, x to the power of negative 4 minus 1. So 2 over 9 remains. We multiply it by the exponent, which is negative 4, and we subtract 1 from the exponent. So what we are looking at here is negative 8 over 9, x to the power of minus 5, and we are going to use the negative exponential rule to move things around. If you have a negative exponent, you can bring it up, make it positive, take it down to make it positive. As long as it's negative, just move it. So we move it down, becomes minus 8 over 9x to the power of 5. ddx of pi squared, again, ddx is the notation from Leibniz. And I hope you recognize the pi squared as e squared, as 1, as 5, as k, as a constant, as a number. Therefore, the answer is 0. Pi squared, e, any number, the derivative is 0. So we are looking at this differentiation formula. F of x is 2, the fifth root of x to the power of 4. Again, we want to use algebraic technique to put it in a format that we can use the power rule, and therefore we are going to use this. The nth root of a to the power of m is the nth root of a to the power of m is a to the power of m over n. That means this piece is x to the power of 4 over 5. And so what do? Well, we follow the power rule. 2 remains. 4 times 4 over 5, x to the power of 4 over 5 minus 1. So one more time, 2. We don't touch that. Times 4 over 5, the exponent, x to the power of exponent minus 1. And this is it. By the way, This is the only calculus step. Everything else is algebra. So this was algebra. This was algebra. This was algebra. This was the only calculus step. And that's important to understand. Now, what do we have? This becomes 8 over 5 x to the power of 4 over 5 minus 1 is minus 1 over 5. You take x to the power of negative 1 over 5 to the denominator and make it to the power of positive 1 over 5. And then you change it to the fifth root of x. So I hope you realize again, the only calculus step, algebra, algebra, another algebra, and this. Okay. So it's pretty straightforward. Prior knowledge of mathematics makes it easy to deal with. Product rule. We are going to use the product rule to differentiate, although this is simple enough that you don't need to, meaning you can distribute and use the power rule. But for practice, I want to show you how this works. And to do so, the first function, we call it f. The second function, we call it g. And I'm going to go with the shorthand notation, f prime g plus g prime f. I'll tell you why I do that, because when you want to do the division, you want to take the derivative of f over g, we use basically the same thing, the conjugate of that, we negate that. So it's, I think, easier to memorize. But if you've already, and I know many have already, learned it in a different order, it makes no difference. So f prime g plus g prime f. So here's the f function. F prime would be 4x cubed minus 6x squared minus 0, which we don't write. That's f prime times g. Just put the g, the blue function, times that, plus g prime. Now, what is g prime? By now we know 3 times 2, 6x minus 5 times f. Just put it next to it. And the reason I'm asking you not to simplify, because I want to emphasize calculus step, and the rest, there are a few more steps to finish it. It's not a finished job. And they're all algebraic steps. Here's another example we want to look at. Y equals x squared times sine x. And to make sure we understand what needs to be done, I'm going to put a raised dot in between, which indicates we are dealing with the product rule here. The product of x squared and sine x, which is going to use f times g, and we are going to go with f prime g plus g prime f. So we start with f prime, which is 2x, times g, which is sine x, plus g prime of sine cosine x. The derivative of sine is cosine, everybody. The derivative of sine is cosine. The derivative of cosine is negative sine. So plus the derivative of sine, which is cosine, and then times f, which is the first function, x squared. Now, before we continue, the way I do differentiation, I don't like to write d dx of this, d dx of that. It becomes too cumbersome. So instead, I write the formula. As soon as I see that, I write the product formula next to me. And I say, okay, this is the f function, this is the g function. I follow the formula. This is the fastest and easiest way. I'm going to rewrite this as 2x sine x plus x squared cosine x. It's really a good practice to bring it up here because x is the argument of cosine, but I don't want anybody to be under the impression that x squared is part of that. In other words, x cubed is the argument, which is not. If h of x is x times e to the power of x, find h prime. To do so, again, I want you to notice we are multiplying two functions, one of them x, one of them e to the power of x. I put a raised dot in between. That's the first thing that we do. So again, I would write f times g f times g, and I would follow the formula. I'm going to write the formula from the memory, and I'm going to follow that. So f prime is 1 times g, which is e to the power of x, plus g prime, the derivative of exponential, the derivative of e to the power of x is itself, so e to the power of x, times f, which is x, and that's the only calculus step. I'm going to factor the e to the power of x out. This gives me 1, this gives me x. So e to the power of x times 1 plus x. Find h double prime of x, known as higher order derivatives of f of x. The derivative of a function y equals f of x is itself a function. Y prime equals f prime of x. Therefore, you can take the derivative of f prime of x referred to as the second derivative of f of x, or f double prime of x, or f inside the parentheses we put 2 and we continue with the next one and the next one. This differentiation process can be continued to find the third, fourth, and successive derivatives of f of x, known as higher order derivatives of f of x. Using the prime notation for derivatives would eventually become somewhat chaotic. We use the numerical notation f, then at top parentheses n looks like an exponent, but it is inside the parentheses. This refers to the nth derivative of f of x. And it's important to understand that, everybody. So having said that, we are going to differentiate again. Therefore, we are going to use the product rule again. The first one, e to the power of x, is the f function. The second one is the g function. And now we are going to take the derivative again, as I mentioned. So having said that, f prime g plus g prime f. So f prime is itself e to the power of x times g, which is the second one, the parentheses, the 1 plus x, or you can write x plus 1, makes no difference, plus g. Now the derivative of g, g prime, The derivative of 1 plus x is just 1. And then times g, which is e to the power of x. Now, if we differentiate e to the power of x, we're done with calculus. If we factor out e to the power of x, this gives us x plus 1, this gives us another 1, so it becomes x plus 2. I'm assuming nobody has any problem with the factoring. H of t is the fourth root of t minus 4 e to the power of t minus cosine t over 2, and we want to differentiate this expression, this function. To do so, first we want to make sure we understand how to do that, and that requires the power rule. We rewrite it as t to the power of 1/4. This one, to make sure everybody can see, this is really cosine, and there's a coefficient of negative 1/2 in front of it. I just rewrite it. You don't have to, as long as you recognize it as negative 1/2 cosine t. So we are going to differentiate term by term. The first one would be 1/4 t to the power of 1/4 minus 1. Minus 4 e to the power of t is itself. Minus 1/2 doesn't go away. The derivative of cosine is negative sine. The derivative of cosine is negative sine, everybody. And again, we are done. We just rewrite it. This one is 1/4 minus 1, negative 3/4. That means 1/4 t to the power of positive 3/4, which is 1/4 the fourth root of t cubed, and the rest easy to follow. So this remains the same, and this one becomes plus. And the reason I put it as sine t over 2, just to make it look like what we had in the first place. Let's look at limits. We want to find the limit of sine 3x, sine 5x over x squared as x approaches 0. We are going to follow the section of interest, okay? And again, I want to mention eventually we will get to other methods. For example, we will get to L'Hopital's rule. So having said that, we are going to follow the rules that limit of sine theta over theta as theta approaches 0 equals 1, limit of cosine theta minus 1 over theta as theta approaches 0 equals 0. So we want to make him look like one of those. Because sine is involved, we want to make him look like that. What is important for everybody to understand is that if you're looking at the sine, if the argument of sine is identical to this one and this one becomes 1, and you cannot change the argument. The argument of sine, you can't change it. So the argument of sine for this one is 3x, for this one is 5x. You can't change that. Okay? So having said that, what changes do we make? Well, The argument is 3x here. So if there was a fraction underneath with 3x, and this one is sine 5x, if it was a fraction with 5x would work. So first and foremost, we cut the x squared into two pieces, and in essence, this fraction becomes two fractions. So far, so good. Look at this argument. This has 3x. This one doesn't. So how do you put the 3x? Well, multiply the top and the bottom by 3. How about this one? Multiply the top and the bottom by 5. Now, please understand this 3 can come out, this 5 can come out, but in any event, we make up two limits using the limit laws. So the 3 comes out, the 5 comes out, the limit for this one, and the limit for this one. Now, it's very important to understand this 3x cannot be changed. We fix this one by taking the 3 in and therefore out. We fix this one by taking the 5 in and therefore out. But what about this one? X is approaching 0. Pass. When x approaches 0, 3x also approaches 0. 5x also approaches 0. And now, take a look. This one, this one, this one, they're identical. So this expression is 1. This one, this one, this one, also identical. This expression is 1. So we have 3 times 5 equals 15. Okay. Now, I can't emphasize this enough. This is the way you truly understand this concept. The argument of sine cannot be changed. So you play around with other things. Same thing with cosine. And the only time it's 1 if these 3 are identical. You have to make them identical, otherwise they're not. So, for example, here, what would be the technique? We notice that we have sine theta over theta. We have cosine theta minus 1 over theta. So if we divide the top and the bottom by theta, first of all, we haven't made any changes because we did the same thing to top and the bottom. And by the way, theta is not 0. Theta is approaching 0. So this piece and this piece, we make up two limits, limits for the top, limits for the bottom using the limit laws. This one is 0. This one is 1 according to the limit of sine and cosine accordingly, and therefore 0 over 1 results in 0. So it's important to write this properly, everybody. So again, pretty straightforward. And I hope everybody is okay with that so we can move on. Okay, now the limit of cosecant x, sine of sine x as x approaches 0, how do we deal with that? We have those, and we also know the relationship between sine and cosecant. Okay, cosecant is 1 over sine. Cosecant secant is 1 over cosine. So we are going to replace this with 1 over sine. And notice what happens. The argument of sine is sine x. The denominator is sine x. And I change the x to sine x. Why is that? Because when x approaches 0, sine of x approaches 0. That's why I can change the x to sine x. But for example, I can't change it to cosine x because that approaches 1. Okay. I can change it to tan x. Doesn't do us any good. So now that they are all identical, those three, you can get to the answer, or you can write it in the following fashion. Limit of sine theta over theta as theta approaches 0, and therefore it's equal to 1. So the proper step to show that if you want to use this, the argument of sine and the other two must be identical. What about the limit of sine x squared over x as x approaches 0? Let's see what we do. Again, when we look at this one, this one, this one, and this one must be identical. This argument, let me erase the work. This argument you can't change. Since we can't change that, we want to make sure everything looks like x squared. So how do we do that? Well, we can multiply by x over x. The denominator becomes x squared. We separate it into two limits, limits of this piece and limits of this piece. So limit of x as x approaches 0, this one. And then the rest of it, this is sine x squared over x squared. This is the second part. The limit of sine x squared over x squared as x squared approaches 0. This is x. How come I changed it to x squared? As x approaches 0, x squared approaches 0, I can do that. I can change it to x cubed, but has to be x squared. And this, according to this, is equal to 1. This is 0. 0 times 1 makes it 0. Let's look at the quotient rule, and we are going to look at a warm-up example. We want to differentiate and we don't want to simplify y equals x to the power 4 minus 2x cubed minus 7 over 3x squared minus 5x. I'm using the same f and g that I used for the product rule. And if I'm differentiating this, I'm going to use the shorthand notation, f prime g minus g prime f over g squared. And I'm going to call the top function the f function, the bottom g function. And now I'm going to follow the formula. Again, those of you who've already learned this, you've seen that they write d dx of this, d dx of that. And that's fine, but it becomes very chaotic and it's sometimes hard to follow. I think this is much easier. So f prime, so y prime is f prime. Just differentiate this, which is, we've already done that. If you go back to the warm-up example for the product rule, it's 4x cubed minus 6x squared. And you're going to multiply it by g, simply f prime g. So multiply by this. Minus. So you see, it's almost the same as that one. So that's why I think it's very easy to memorize it. Minus g prime. Now, g prime is 6x minus 5 times f, the numerator, over g squared. So there's really not much you have to just write the bottom in a parenthesis and square it. And you're done. As far as calculus is concerned, of course, you have a few more steps to go to finish the job. That's not what I'm interested. I want to show you that the calculus step is really not involved. There's not a lot of steps. Here's the next example. We want to differentiate, obviously. Do we have to use the quotient rule? And that's what I want you to pay attention to. If you need to use the quotient rule, as it was the case here, and you try to avoid it, you make it more complicated. I promise you. On the other hand, if you don't have to use the quotient rule and you don't recognize it and you use the quotient rule, you do the same thing And if you don't see the easy way out, most likely it's going to be hard to finish the job. I hope you recognize this as two fractions. One of them is 10, one of them is minus 7x. And obviously, the derivative is minus 7. So it goes extremely fast if you see the easy way out. Y equals 1 plus sine x over x plus cosine x. Clearly, we need to use the quotient rule. So I'm going to write this formula next to me again from the memory. F over g is f prime g minus g prime f over g squared. And I'm going to write this f. I'm going to write g next to this. So I know this is the f of x function. This is the g of x function. And I'm going to start the quotient rule with f prime. The derivative of 1 is 0, sine is cosine x. So cosine x times g. Just put the g, the bottom here, x plus cosine x. Minus g prime, x gives you 1, cosine gives you negative sine. Times f, just put the numerator here, and that's practically the end of it, because the bottom, you just write the same thing and square it. All right, done with calculus. Now let's finish the job. By using our algebraic techniques, trigonometric identities, and so forth. So what are we going to do? So this is x cosine x, this is cosine squared, and I hope you realize this as a minus ba plus b. The answer is a squared minus b squared, or 1 minus sine squared. Now, what about 1 minus sine squared? Let's remind everybody of Pythagorean identities in trigonometry. Sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. So if sine squared plus cosine squared is 1, clearly 1 minus sine squared must be cosine squared. And so we can get rid of those two. And we are practically done. Y prime is x cosine x over x plus cosine x quantity squared. Derivatives of trigonometric functions. Prove d dx of tan x is secant squared. Let's remind everybody of what we said about trigonometric functions. The derivative of sine is cosine. The derivative of cosine is negative sine. You can look at the proof in the lecture, and it uses trigonometry and geometry. Now, the rest of them are easy to prove. Actually, one of them you use the information over there, and the rest of them use trigonometry to finish the job. And so the derivative of tan x is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant x is secant x tan x. The derivative of cosecant x is minus cosecant x cotangent x. So let's look at the derivative of tangent equals secant squared and prove that. So we are going to say y, or f of x, is tan x, and we know tan x is sine x over cosine x, because We remember from trigonometry, tan x is sine x over cosine x, or 1 over cotangent x. Cotangent x cosine over sine, or 1 over tangent x. Secant is 1 over cosine, cosecant is 1 over sine. So having said that, we write it in the form of a sine over cosine, and right away we recognize we have to use the quotient rule, so we call it f over g. And therefore, we have f prime g minus g prime over g squared. So f prime sine, the derivative is cosine, times g, which is cosine x, minus g prime, the derivative of cosine is negative sine, and then times f, which is sine x, and just write the bottom and square it, cosine squared x. Done with calculus, we are going to continue finishing off by rewriting this as cosine squared. This one is plus sine squared. We know they add up to 1. And if it's 1 over cosine squared and uh, secant is 1 over cosine, secant is 1 over cosine, therefore 1 over cosine squared must be secant squared. So as you can see, trigonometric identities basically I went over for you that will help you do the math here. Let's continue with secant. We said the derivative of secant is secant x tan x. Secant x tan x. Why don't we prove that? So to do so, the function y is secant x, which is 1 over cosine x. And we are going to use the quotient rule on that by rewriting it, by writing as f over g. So we need f prime g minus g prime f over g squared. So f prime is 0. F prime is 0 times g, which is cosine x, minus g prime, the derivative of cosine is negative sine, times f, which is simply 1. And just put the same thing down here, square it, cosine square. So what we are looking at, this is 0, this is negative times negative plus sine over cosine square. We cut it into 2 pieces. This one, we are going to write 1 over cosine times sine over cosine. 1 over cosine is secant. Sine over cosine is tangent. And that's the proof that the derivative of secant x is secant x tan x. And I highly recommend you practice maybe working on cosecant or cotangent or things like that as an example. Y is 1 minus secant x over tan x. To differentiate, we are going to use the quotient rule and write f over g and work on that. So first f prime times g, then minus g prime times f. So what is f prime? 1 doesn't do anything, minus remains. Secant gives you secant x tan x. So negative secant x tan x times g simply times tan x minus g prime, the derivative of tan x is secant squared, times f, just put the numerator next to it, and then the denominator is squared tan squared x. And again, let me put asterisk next to it, and I really can't emphasize this enough. You're done with calculus, okay, everybody? The number of steps for calculus is minimal. So we're done with calculus. Let's finish the job. So this one is negative secant x tan squared. This one is negative secant squared. This one is positive secant cubed. The denominator remains unchanged. As you notice, we can take the common factor of secant x out. If I do that, this gives me negative tan squared. This gives me negative secant x. This gives me positive secant squared. Again, the denominator is unchanged. So take out the common factor of secant x. Negative tan squared minus secant x plus secant squared. Now, reminding everybody of one of those Pythagorean identities, we know 1 plus tan squared is secant squared. So if I move the tan squared to the other side, I write secant squared minus tan squared or minus tan squared plus secant squared. They add up to 1. So I can replace these two pieces with 1. And this is secant x times 1 minus secant x over tan squared x. You're done. Sometimes in trigonometry, they may want you to write everything as a function of sine and cosine. You can change them accordingly and simplify them further as function of sine and cosine. It can be done. Find the points for which the tangent lines are horizontal. F of x is given as x cubed minus 3x squared plus 5. Horizontal lines, the slope would be 0. And to find the slope of tangent lines, you have to differentiate. So in short, first and foremost, let's differentiate this and find f prime of x, which gives you 3x squared minus 6x on the one hand. On the other hand, if they are supposed to represent tangent lines that are horizontal, that means the slope must be 0. That means you set this one equal to 0. And to find it, obviously, you factor the 3x out. X is either 0 or 2. So those are the 2 points, just to make sure we don't make a mistake, that they represent 2 points, rather not the pair 0, comma 2. If you put the 0 here, you get 5. That's one pair. If you put the 2 here, 2 cubed with the 8, 2 squared, 4, minus 3 times that, 12. So 8 minus 12 plus 5 becomes 1. So 2 comma 1. Those are the 2 points that we need.